Hello, I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, 2049 Outfitters.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and the time changed, so it's 4 a.m. on Saturday in London, 12 noon on Saturday in Hong Kong, and so forth. We're broadcasting live from Thousand Oaks, California. Tonight we have crunchy topic, White Dwarfs. We'll be back in 8.3 seconds. During this episode, Jeff will delve into white dwarfs. Dwarves, I don't know. Our inclination is to add stars to the end of that, but they're not actually stars. Rather, they are degenerate stars. What the heck is that? Stay tuned to find out. How do they form? What is their structure? How do they die? What can we use them for? And I see comments, so let's go there.
Yeah. Hi, Janie.
Hi, Janie. Welcome. Thanks for being here with us.
Someone new.
Hi there.
Hello.
Welcome. So, Jeff, what did you learn doing your research this week?
Well, lots of things, actually. Can you show screen?
Yes.
Okay. For one thing, this is what a white dwarf, we call it a star. It's common usage. I'll probably keep saying that too, but it's the remnants of a star.
Well, and when we did a search to find out more information, if you didn't add white, star to the end of it, you'd get other things. So, hey, Dawn's here.
Like references to Game of Thrones or something like that.
Hi, Dawn. Welcome.
But so this is the size of a white dwarf compared to the size of the Earth. Now, maximum,
very dense, right?
Yeah, maximum size of a white dwarf is around 1.3 something times the mass of the sun.
So a bit bigger.
Yeah. Well, 1.25 to 1.5 times the size of the sun.
Okay.
But this is the size of it. Now a white, and I just wanted to show you this just because I thought that this was really intriguing, that something that massive is that size. Here are just some images that I found. Nothing great, but
these are mostly, they look like artists.
Well, no one's really got a close up
right.
of a white dwarf.
Hey, Scott's here.
Hey,
hello, Scott. Welcome. Thanks for joining us.
Yep. So the usual thing, a white dwarf is the remnants of a star that's no more than 9 times the mass of the sun.
Okay, so not super huge.
Yeah, anything bigger than that, and it's crushes down to a neutron star or black hole.
Okay.
But it's up to 9 times the mass of the sun. But as I said, the maximum mass of there's
is the stellar. Go ahead.
Yeah, is the stellar remnant still iron at this stage, right after the end of the red giant phase, or have the atoms already been changed into something else already?
Well, iron is the end of the road for the chemical reactions within the star. That's the last thing that until it blows up.
Yeah. And being the end of the road, it's not really the most common element there. The most common element in a white dwarf, in fact, it says it here somewhere, carbon and oxygen. And the other elements that are produced are usually produced in the because remember, these are not supermassive stars. These are not supermassive stars. So once they get rid of their hydrogen fusing, they have a brief helium fusing phase.
How many millions of years?
Yeah. But
brief for stars.
But then they blow off the outer layers, and the blowing off, the fusion that's involved in that does create a lot of the heavier elements.
Okay.
But they're basically blown off. So what you've got left is mostly oxygen, mostly carbon.
Okay.
And so from 9 times the mass of the star to, 1.34, times the mass of the sun. Oh, go ahead. No, it doesn't. No, it's not. It's never as clean as you might think. There's
Just
a lot
because
of
of the
stuff.
mass, it's a smaller.
There's a lot of stuff going on. Yeah.
Okay.
And there might be some that.
Great question.
Yeah, there might be some that are just the right size to do that, but there's so much going on that usually something tips it over and it blows before it can do that.
Okay.
But there is an awful. But the heavier elements do end up in the center. So the stuff that's being produced does tend to go toward the center unless it blows up too fast. Then they're all there. But that's why you've got carbon and oxygen in the center, because they're relatively heavy.
Okay.
But they're also, for a light star, which is, up to 9 times the mass of the sun, which is actually fairly light. In fact, there's a graphic.
That's kind of cool. It says there's an image of. Let me put it up again.
Yeah.
I'm reading it. It says that image there is. Go ahead.
Of a white dwarf, yeah. And let me zoom down. Sorry, I'm trying to find a certain graphic that I saw down here.
Okay. I can wait to pop it up if you.
Oh yeah,
should
probably do
next
that
time. Okay. Just so we don't make anyone dizzy. Let me know when you're ready.
Yeah, go ahead. Yeah, no, not yet.
Okay.
I'm still looking for that graphic. I'm hoping it's in this one. Otherwise, I just made everyone seasick without having something to show for it, and I think I did. Because there was.
That looks like a long page, though.
It is. Okay, I can't find it here.
Maybe you get this reference. My man be scrolling like Usain Bolt.
Yeah.
I don't know what that is.
But
what is that?
I forget, but
okay.
I know
He
it's
knows.
a reference. And I'll probably end up looking it up later because I can't remember.
Okay.
But I saw a really good graphic, and I couldn't see it here, that showed types of stars and what they turn into.
Oh, okay.
Yeah, so
maybe it'll show up in your.
Yeah.
So I know he lines up a bunch of tabs to demonstrate well.
Red dwarfs and yellow dwarfs, which is what our sun is. It's actually a dwarf star, as opposed to giants.
Go ahead and find the diagram with the.
Oh,
that one. The HR diagram, otherwise known as.
Yeah, main sequence dwarfs. This is what the sun is right here.
Right.
And subdwarfs, and these are the white dwarfs down here. After they've blown off. What? Oh,
he's got spots. Yeah. So Usain Bolt is a Jamaican man who ran the 100-meter fastest about 10 years ago. Yeah. Got that.
Yep.
Cool. Thank you for.
I knew the name, but yeah.
Yeah.
Thanks.
Okay.
So, saw a graphic.
So well, let's go back to Hertzsprung Russell is the name on the bottom there, and we shorten it to HR diagram.
Right. So basically, stars like our sun and slightly bigger can become white dwarfs. Red dwarfs become white dwarfs. Not as dramatically as ours do, because they don't really blow off a lot. They just start, they just stop fusing. Although I don't know if we've seen many of those, because red dwarfs last a very long time. So theoretically, they become white dwarfs. Now, brown dwarfs just kind of peter out.
Yeah.
They don't become white dwarfs. But anything bigger leaves a core that's so dense that it compresses much farther than as a white dwarf. And what happens?
Oh.
What's it?
You're doing a demonstration now.
Okay.
I'll get you on here.
The core, since it doesn't have the fusion, the heat of the fusion to support it, collapses. And it blew off all the rest of it. It collapses down to the point, unless it's above a certain weight, down to the point where essentially it becomes a soup of nuclei and electrons.
Oh.
And it becomes essentially a plasma.
Ah, okay.
But it's under such compression that the electrons, which like to be farther away from things, end up getting pushed into each other. And there's the Pauli principle, which says two electrons of the same quantum state can't occupy the same space. And that is the pressure that keeps it from collapsing further.
Oh.
Is that you can only have so many electrons in the same spot. They have to, in the same spot, you can have more than one electron, but they have to be at different quantum states.
Ah, but there's no longer fusion happening in the center of this thing, right?
And that's what makes it not a star.
Is that what makes it a degenerate star?
Yes.
Okay.
There's no fusion. Now it's still producing heat and light.
Interesting.
But all of that
plasma, I guess. Okay, that makes sense.
But all of that heat and light is from the compression. It's from the energy of the compression.
Not fusion.
Right.
Okay.
So essentially, it's like a hot coal. Except that it is kind of sort of producing energy as it compresses. But by the time you see it as a white dwarf, all of the compression's done and it's just really, really hot.
So it's cooling off, essentially. It's
right.
going to cool off for a very long time. In fact,
yeah. And
we probably haven't.
White dwarfs are actually, because the electrons are all free, it's a superconductor of both electricity and heat.
Okay.
And since it's a superconductor, heat likes to stay in it. And vacuum is actually a very good insulator.
Yes.
So it only loses heat at the black body radiation.
Okay.
So it loses heat at a very predictable manner and very slowly comparatively. So it stays.
Could it be a clock?
Yeah, it could be, because as they get cooler, their color changes. They stop being white at a certain point, start going down to blues. Go ahead.
We have another question. They're coming fast, and thank you so much. So the sole fuel source of the white dwarf is potential energy that comes from the gravity of the dense core remnant.
Yes, that creates the energy, but by the time we see it as a white dwarf, it's no longer potential energy because the collapse has already happened and it just heated stuff up so hot that it's done. It's just not hot enough to trigger fusion, but all of that energy is stored there, and it just stores it very, very well because it's a superconductor for heat.
So it really does sound like a coal in the fire that's just sort of dying out now.
Right, except that the coal can hold a heck of a lot more, can hold not nearly. Yeah, okay, yeah.
Wonderful questions.
Yeah.
Thank you so much.
And so, so it just sits there and radiates. And
sounds like a pretty good power source, actually.
Yes. In fact, we mentioned what could we use them for? Yeah. Yep.
Oh, okay. So he's saying yes to this.
Yep.
It's like a hot ingot. No forge, no fusion.
Right. Yeah. Yeah. You took it out of the forge because the fusion stopped.
Very good. Thank you.
But now, can we take a piece of the white dwarf off? Well,
unlikely.
1 cubic centimeter of white dwarf is more than a metric ton. Yeah. So you're not getting it off of there. And plus it'd be very, very hot. Because even though the white dwarf isn't dissipating heat fast because the vacuum is a pretty good insulator, as soon as you touch it to try to pull some off, well, whatever you touch it with is a much better conductor of heat than the vacuum. So it's going to basically melt, vaporize, whatever.
All right. Gosh, we're on a roll here. I love it. Thank you. It would take a lot of energy to remove a piece because the dwarf spins quickly and has a lot of gravity.
Right. The gravity, because of the mass, the spin would actually help you sort of. Because the spin would give you some kinetic energy that would offset. In fact, a spinning white dwarf, which I can't imagine that there aren't any that don't spin. I think since every star that we've seen spins, I would imagine that all white dwarfs, since as things get smaller, they spin faster.
Like pulling your arms in.
Yeah. I would think that
this ice skater.
That a non-spinning white dwarf would be a very specific case.
Mm.
You know, it'd be like, oh, there's one of those. You know, we haven't seen one of those before, but they're mostly spinning. So that's why I was kind of ishish on the 1.3 something times the mass of the sun for a white dwarf. If it spins, it can have more mass because the spin actually pushes some of it away from the so, you know, and if it had more than that mass, the quantum states of the electrons would not be enough to keep them from smashing down into the protons. And once you push the electrons into the protons, then they become neutrons.
Okay.
Thus, neutron star. And that's what that is, if it's heavy enough to do that. So,
what would change its classification, basically?
Yeah.
Okay.
So yes, if you wanted something that would gather energy from a source, you would want to put it, and you were thinking really long term, you would want to put it around a white dwarf, because even though red dwarfs are very long lived, since there's not much mass there, they're got solar prominences out the yin yang from them.
Oh, they do.
Yeah. Oh, they're constantly bubbling and very long.
I didn't realize that.
Yeah.
What about the white dwarf?
Nothing. It's so heavy that it's just still there.
All right. We got another comment. You ready?
Mm-hmm.
If this has to wait until later, that's totally fine. But I wanted to ask, how does the mass and metallicity affect the elements that are made in the supernova and those that are left over in dwarf? Ooh, I like it.
That I'm not too sure about. I don't think it affects the white dwarf quite as much in the major. I mean, it becomes like they do talk about different impurities in the white dwarf. So heavier metallicity would have more impurities.
That's really anything that's
right
more than hydrogen and helium, basically. They're considered metals.
Yes. Oh, Scott. Yeah. In fact, that's one of the things that I was thinking about. Yes. Would it produce enough light and heat? Yes. Now, the Goldilocks zone would be very different from, and the trouble is that it would produce light, heat, and radiation. And so you'd want to be careful about that. Oh, yeah, go ahead.
We got another. Okay, no worries. Honestly, this may be poorly researched, and I'm just a casual observer.
Well, so am I,
That's
actually.
Wonderful.
Yeah, so
That's
am
where
I.
everything starts, by being interested.
Yep, I got interested in them, so I read up on them, and so now I'm sharing. I'm not an astrophysicist,
no,
and I don't play one on TV or even here.
No. Computer expert.
Right. Yeah. So Scott was saying, can it support life on a planet? They have found planets orbiting white dwarfs. Basically, the remnants of planets like Earth or something like that, that basically are cinders, because during the red giant phase, it cooked the planet off.
Yeah.
Now, could you reintroduce life to those planets? Put atmospheres on them? Yeah.
If they're in the right place, right?
Yeah, but if you can put atmosphere on one of those planets, you can put it in the right place.
That's true.
And if you're going that route, make a Dyson sphere around one. It's so stable.
Probably easier.
Yeah. No, it's not, actually.
No? Okay.
You have to bring mass from a whole bunch of other solar systems to make a Dyson sphere.
There might be stuff in that solar system, that system too.
Yeah.
Okay.
But because it's so stable, because all it's doing is sitting there radiating. There's no messy stuff. I won't say no. Actually, I shouldn't say no, because there is some messy stuff, but it doesn't do much out on the outside. All
right. If this is a tangent, no worries. We love tangents.
That's our show.
But I wanted to ask, Why red dwarfs flare so much? Ooh, I like that question.
Oh.
Maybe because they convect so much more?
Yes, because they're relatively light compared to other stars. I mean, a red dwarf is just teetering on the edge of just enough mass and, pressure to fuse, but then having the fusion blowing stuff out. So it's just, they say that our sun is at a balancing point because that's where its radius is. A red dwarf is smaller. The balancing point is a lot less stable. And they'll
and it's the difference between gravity pulling in and pressure pushing out.
Heat pressure.
That's the balance.
Right.
Jeff's talking about.
And yes, because they have convection and stuff like that, it's a much bigger part of it. Not, our sun has convection, but the gravity and the gravity pressure,
they've gone through this
is
oscillating phase, I guess.
Yeah, the sun oscillates, but think of this much oscillation on something much smaller. It's a much bigger oscillation compared to the piece of it, and the chance of some of it getting far enough away that the oscillation back is too far away to actually come back. Like a CME from our sun.
Okay.
Basically they have a lot more CMEs because there's not as much pressure. If it gets just a little bit far,
pressure or
pull, not
gravity.
Pull,
gravity, basically.
Yeah, it's kind of like playing golf on the moon. You have to be careful.
You could launch it.
Yeah.
It does have gravity and it will come back down, but only if you do it right. All right, Dawn comes in with, it's okay. Just remember that supernova result from massive stars and white dwarfs come from smaller stars.
Yeah, although they do nova to, like stars like our sun will nova and blow off and become a planetary nebula with a white dwarf.
Nova.
Eventually, yeah, it'll blow off.
Oh, nova, not supernova.
Not supernova.
Yeah.
Yeah, it'll blow off, the outer layers of it and become a white dwarf.
Oh, here we go. I am excited to see more results from that new solar probe. I think the sun has many long period oscillations that we don't know about yet. May affect the weather significantly. I agree.
Yeah.
And what, I don't think I caught wind of this new solar probe. Or did I?
Yeah, we mentioned it a while back when it launched, but it had a long ways to go, so it's been out there for a while.
Oh, good. I like this when there's
between. I was we've basically remember Apollo landing on the moon, so we've been fascinated for a very long time.
Yep. Yeah, we watched as kids.
Yep.
All right, you got anything else on that?
Yeah. Okay. Lots.
Okay. Good.
Okay. So.
Oh wait, you want me to share, or you want to scroll?
I'll scroll and get to another section here.
Okay.
Okay. Let's see this.
Yep, it's up.
Okay. The water. What's density in kilograms per meter cubed? Water is 1,000. Osmium, one of the heaviest elements that we've got.
I'm guessing somebody made in the lab.
No, it actually exists.
It's a natural. Okay.
Yeah. 22,000.
Wow.
The core of the sun, 150,000 kilograms per square meter. A white dwarf, 1 times 10 to the 9.
My goodness.
Now here's the interesting thing. An atomic nuclei is 2.3 times 10 to the 17. So that's very, very dense. But then it does, you don't have to take into account the distance that an electron, comes from it. So then a neutron star is 8.42 times 10 to the 16 to 1 times 10 to the 18.
That's its range. Okay.
Yeah. And a small black hole is 2 times 10 to the 30th.
But a supermassive black hole.
Hey, hang on. Why are they even talking about density of a black hole?
And he comes back with, wow, that's 1 million kilograms per cubic centimeter.
Yep. Yes. Yes. Yeah. That's.
Whew.
Yeah, that's why you're not going to be putting it in your pocket. Well, aside from the fact that it'd roast you. Um, but yeah, unfortunately, trying to stand on the surface of a white dwarf basically means that you're a thin paste, a thin paste of carbon on the surface of the white dwarf, because
Maybe.
it fry you and crush you.
Sounds like he'd be just sublimated, maybe even.
Right? Yeah. Okay. So,
All right, what else you got for us?
let's see.
Tell me when you get there.
Let's see if there's anything interesting left on this
That's
one.
a big long page.
Right. Yeah.
That's a lot of stuff. And what's at the top? Just white dwarf.
Oh, yeah. This is.
He comes back with would still weigh hundreds of pounds in a chunk as small as the naked eye can see. Amazing.
Yep. Yes.
Yeah, Hot pocket.
Yes.
Yes.
Yeah. So we're never going to really be able to play with white dwarf matter.
Mm.
And it'd take super science. It would take science on the order of magic. Compared to what we know. Because it was Arthur C. Clarke that said any
sufficiently advanced technology
looks like magic.
Yeah, something like
and
that.
Of course, I forget someone who came up with the corollary of that. Any sufficiently advanced magic looks like science. Okay, so this is to answer Nee's earlier question about mineral-rich white dwarfs.
Metal-rich.
Metal-rich, yeah. So they're about 20 to 33% of white dwarfs have metal lines in their spectra.
Ah.
No, that means that there's enough metal for it to actually show up.
Don says, yeah, I was wondering what we would pick that WD mass up with.
Yeah.
White dwarf mass. There it is. Okay.
For one thing, it'd have to be robust enough to not melt or vaporize when you touch it.
Right.
For another thing, it has to be strong enough to not get crushed. But so metal-rich white dwarfs, only about a quarter to a third of them have enough metal in them to actually pick up in the spectra.
Ah.
Now, that could be that the heavier elements sink. If the heavier elements sink to the bottom, to the center, you won't pick it up because you're only reading this outside.
Okay.
That's why most of the ones that we see are carbon, oxygen, and a couple of other nearby elements.
Okay. Sounds like they're actually light enough to be anywhere but the center.
Right. Yeah. And if you show here.
Okay. You ready?
Yeah.
Here you go.
This is off of that same page, but you've got carbon and oxygen. And so here's iron. So yeah, it is very close to there, but the iron's at the very last stage. So it's either buried in the core or it gets blown off, but most of the structure of it, I don't know why there's not a lot of nitrogen in these, but they don't seem to be. Maybe the fusion just doesn't work out right for getting nitrogen for the kind of fusion that you see. But so helium, carbon, and oxygen are what we see.
Dawn says iron turns into protons and neutrons. Okay.
Okay. And then so here, magnetic field, huge magnetic fields, because these are superconductors. They're rotating.
Yeah.
They're really huge magnetic fields. Again, will we ever get close enough to really experience one? Probably not. But that's another reason why you won't be picking stuff up off of it, because the radiation of the magnetic field will probably kill you before the heat and the gravity does. So yeah.
So robotic at best.
Thought to have a surface field of approximately 300 million Gauss.
Okay.
Yeah. So not, it makes Jupiter look like a dead zone.
Okay.
And so I talked about its degenerate matter, and that's what electron degeneracy here. And that's what happens when the electrons collapse so much that they that they try to occupy the same space. And basically the lower energies of the quantum states of electrons will fill up. And that leaves the, more, that leaves the higher energy states, and then those fill up, then, eventually, and that's what happens. So the more mass you have, the hotter it gets, because the electrons are whipping away, because the electrons that are free to move are whipping around so much faster. And the pressure on it, the outward pressure from that, is actually higher. So the more massive, the smaller the bigger the white dwarf, because the electron pressure is actually higher. It's a little bit weird.
Yeah, that seems to work a little bit backwards.
Right. Yeah, but and then this talks about, and I'll throw up links for these pages in the next section. Because this article talks about electron density degeneration, which is what white dwarfs experience, then neutron degeneracy, which is what we were talking about for neutron stars, and then quark degeneracy. That's what happens with black holes when the quarks cannot push against each other enough to hold themselves out. Then it becomes a black hole. So, and now here's a decent article from Astronomy. Basically covers what it's a restating of the wiki article. So, it's good, but
yeah, we see that a lot.
Yeah,
Lots of good sources, lots of similar information.
Yeah, and here's space.com. It has some facts about white dwarfs. We've covered pretty much all of the ones that they talk about.
Great image.
Yeah.
Don't know how accurate it is.
Right. And just this is NASA's Hubble mission team, and this is the limit of their article. So I'll share it, but I'm not really going to talk about it much. Now, what happens when a white dwarf gets old? It actually crystallizes from the center out, because that's where the most pressure is.
Okay.
And there were articles about black holes or white dwarfs turning into diamonds. Well, yes, there's carbon, but it's mostly oxygen. So, it's not really diamond, but it is a crystal. And it'd be really neat, a really neat crystal.
Yeah.
But, it's also super dense.
Yeah.
In fact, if you manage to get some off of the white dwarf, it'd probably explode.
Oh.
So without the gravity to hold it into its crystalline form, it'd probably explode pretty good.
Yeah.
But and the crystallization actually slows down the heat dissipation. Yeah.
Okay.
Yeah.
Oh, most truthful media headline.
Yeah. Yeah, the diamonds thing. Yeah. There might be one out there that does that, but just because it'll have just enough more carbon than oxygen that, yes, you might get something that looks like a diamond, but it still won't be a diamond.
So what are the ratios? You think it's like half and half most of the time?
I don't.
Okay.
I don't know.
You didn't come across that with your...
I did. I don't remember, and I don't want to say it.
Yeah.
I don't want to just...
You'll get the links.
Pull a number.
You can look it up yourself.
And at least the wiki article has a lot of references, so you can follow the rabbit hole.
Yeah.
But so they did discover that this crystallization is happening, and it actually slows down the heat dissipation.
Wow. I guess it's like heating up a rock, which radiates, which continues to keep you warm.
Yeah. So it threw off their numbers for the ages of white dwarfs, because as they get cooler, the color shifts. So they can tell how old a white dwarf is by its color. Now, it doesn't change much, but it does change. And so previously, just from the color of the oldest white dwarf that they found, they did get a maximum age of the universe of 13.5 billion years, just from the white dwarfs. So that actually kind of meshes with other methods of getting the age of the universe.
It's a good way to calibrate that. Yeah.
Now the fact that that the crystallization slows that down might throw off that 13.5 billion years.
Maybe.
So
maybe a little bit.
Again, the more you know, the more you find out that you might not have had it quite right.
Everything we learn develops more questions than we started with. I love it.
Yeah. And
what else you got? Wait. Let me share.
This is that stupid cosmic diamond thing.
Okay.
Science alert.
Science alert.
Yeah.
Ooh.
And here's one where buoyant crystals could halt the cooling of white dwarf stars for a while.
Buoyant crystals? Less than the weight of water?
Well, when it doesn't form.
Wait. Let me come back to you.
When it doesn't form right in the core, the crystals might actually be lighter than the plasma, the plasma soup of the neutron star.
Okay.
So they'd rise up to the top.
Okay.
And they're saying that could, they call it a solid liquid distillation mechanism. I'll put this in here.
We'll give you a link.
You can follow the footnotes to your. I can't actually.
Oh, you can't?
Because this is nature.com.
Yeah. Oh.
Unless you have access to a university and can get the full article. Yeah, this is a paywall. In fact,
that's too bad. But we could get a screenshot of it and.
Yeah, but this. So I can get you the link if you have. But yeah, we can't get to the full article. How are you
in there?
I don't have the full article. It cuts off.
Oh, I see.
But it's $30 for a month.
Yikes.
To get Nature and 54 other portfolios, or $200 for a year for just Nature.
Wow.
Or $1.95 an article.
Because it depends on your need. You ready for a comment?
Yeah.
All right. Thanks again. The crystal lattices, the elements and compounds arrange themselves into depends on temperature and pressure. So diamond may not be the correct crystal for the carbon in a white dwarf.
Right. And
I like it.
Yeah. And
with all that oxygen in there too. That's plenty of pressure though, it sounds
right.
like.
And if you think about it, you could very well have crystallized oxygen, which,
I know you can liquefy it. That's called
you can freeze
liquid oxygen.
Yeah, you can freeze it too. But to crystallize it, would take a lot of pressure.
A lot of pressure.
Yeah.
Yeah, I mean, it's possible.
Right. So if anyone has access to a university, you can get the full article.
Very cool.
All
right.
And just because now that we know that they exist and can look for them, thousands of stars observed turning into crystals for the first time. Because now that we know what to look for, we're going through a bunch of stuff saying, oh, there's one, there's one, there's one, there's one.
So it's a slight shift in the spectrum? Is that
Okay. Yeah.
All right.
And
so I did understand that correctly.
Yeah.
Okay.
And so, so they're now finding that this is not an uncommon thing, that this is part of the life cycle of a white dwarf. That's
cool.
And
that's how we discover things.
Because there's more pictures of white dwarfs.
Most look like they're
artwork. None of these are.
Well, the one was the one at the top in the.
Yeah.
That was from Hubble from before.
Yeah. But so these are, if you want just images that look neat. But my favorite is actually just this one right there. White dwarf Earth.
To scale.
Yeah.
That's the important part here.
Yeah.
To scale.
Yeah. Oh, and this is a light one that's 1 times the mass of the sun.
Wow.
So so that's
mass of the sun, size smaller than the Earth.
Just barely. I mean, it's close enough to.
Yeah, it's pretty
close enough for government.
Earth's like a supermoon.
Yeah.
There's a mini moon now too.
Yeah.
I guess the supermoon is when it's kind of closest, and then the mini moon is when it's farthest away.
Oh, I thought there was a new moon.
What I'm saying is
the mini moon, as in the mini me.
No, this is the perigee thing. Okay.
Yeah.
All right. Anything else you got for us?
Not right now.
This is
if
fascinating.
you keep having questions, I'll keep trying to find the answers to them, and then
Excellent.
I'll start posting the links. If you want to do.
Yeah. Do we touch on all these things? How they form? What is their structure?
Oh yeah. What could we use them for? I want to build a Dyson sphere around one.
Yeah.
But then I think long term.
Yeah.
Because white dwarfs should. Oh, what happens to white dwarf when it loses all of its heat? It becomes a black dwarf. Basically,
right.
no longer. That's why brown dwarfs are. When we talked about brown dwarfs, I was black dwarfs was already taken as a theoretical end life of a white dwarf because it no longer produces light.
Because
theoretical
because
you
told me.
Yeah, because the universe hasn't lasted long enough for a white dwarf to lose enough heat to become a black dwarf.
And that's basically how it dies.
Right. Yeah.
Okay.
And the oldest white dwarf still probably has about 13 billion years on it before it stops radiating.
Don't hold your breath.
Yeah. Yeah. So
we may never know.
And even a black dwarf will still be phenomenally hot. It just won't radiate because these are superconductors. Okay. It retains a lot of heat. And when the pressure of the heat to leave is lower than the insulating factor of the vacuum, it'll just stay.
Okay. So
they estimate that even a dead white dwarf will still be about 10,000 degrees Kelvin.
Kelvin.
Which is, plus or minus a couple hundred from Fahrenheit or Celsius. I mean,
yeah, I'd have to look it up.
So that's really, really hot, but it's not radiating anything because the heat can't escape. Now, if you accidentally landed a rocket on one, aside from it still has its mass and it'll crush, yes. It's still hot enough to melt the rocket, even though it's not radiating anything.
Wow. So, mind-blowing.
Yeah.
All right.
So I will start putting these links up there.
Excellent. Thank you. And when Jeff adds the link, if he copies, pastes it, it should be clickable for you.
Yep.
Let's see, it'll show up in YouTube and a couple of Facebook's websites.
Yeah.
Facebook pages. Sorry. All right. So while he's doing that, I'm going to tell you about some stellar events this week. We're talking about March 15th through March 22nd. We actually missed one for you last week. Sorry, but happy Pi Day belatedly. Oh, we got a comment. That's 18,000 degrees Fahrenheit.
Yeah.
Thank you very much. That's why we love you so much, because you know things, you look them up for us, and you share. All right, we got one from Dawn, too. I was hoping you were going to talk about the planet remnants they've been finding on the surface of white dwarfs. Oh right.
Yeah, yes. Anton talked about it.
Yeah,
yes.
Anton recently. Yeah, we saw that, right?
Yeah.
Go ahead. I'll talk about Pi Day later.
Yeah. Look up Anton Petrov.
Petrov. Petrov. Mm-hmm.
Yeah, look him up on YouTube. Really good stuff. Look for his white dwarf thing.
I think you could do a search in there.
Yeah.
And I bet it shows up with white dwarf.
What they did was they found smears of planets on the surfaces of white dwarfs. Basically,
I guess when
planets that augured
expanded, right?
Yep. Yeah. Planets that augured in.
Okay.
Just because their orbits decayed enough that they augured in. And they found a smear of basically, planetary material on the surface of a white dwarf.
Thanks, Don. We forgot. We were thinking about it earlier, but
I was, but I was gonna point to the Anton thing because he covered it so much better, and had the time to cover just that one thing. So
yeah, we really appreciate his videos.
Yeah,
he'd make a great guest too. We would love to have him on our show. Anybody know how to get a hold of him? All right, so we missed one last week. That was Pi Day. Jeff's adding some more links for you. March the 17th, the moon rises high and Neptune and the sun are in conjunction. March 19th is the vernal equinox. March 21st, Venus and Saturn are in conjunction. That's in the morning. March 22nd, we have the Friday night show again, and we have a guest this time. You can find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel. What inspires you the most for the coming week? You look like you're still busy. Should I do the other part too?
Oh, yes, please.
Okay, so I'm going to go ahead and, I don't think I set it up right. Yep, I'm at the wrong end. All right, so I find these things. Go ahead and share. Yeah, I'm over here. I find these things and I decided I will just tell you about other events and activities and stuff. And here's one of them. Audience with an astronaut. You can register below for an upcoming session. I think this is online. This program will feature a variety of different astronauts throughout the school year. Each session will include an inspiring interview with the astronaut, Q&A for students, and a STEM hands-on activity with downloadable activity lesson plans. See below for specific sessions information and to register. And we can see the list right now. Upcoming sessions. Well, that's past February 26th. The 19th is the next one. Here we go. Tuesday, March the 19th, Future of Solar Weather. And they specify grade level. In this case, is 3rd to 5th. And 3rd to 5th. And here, this is for everybody. Students will learn about space weather, what it is, how it's formed, and how it impacts life here on Earth. And oh, yay, it's Eileen Collins. How wonderful is that? And she's going to talk about the solar eclipse and STEM careers. All right, that looks wonderful. Oh, we have a to be determined for the date, 6th through 12th grade, lunar outpost looking ahead. Okay, it's register here. And they have previous ones. Let me go ahead. Oh, it looks like you can see them. Yeah, session video recording. So if you want to watch past ones, looks like we're over here. I did find these recently, so I don't know a whole lot about them. Let's click register, see what we get. It's going to take some time. Oh, no, here we go. Audience with an astronaut. Yeah, it looks like it's a Zoom thing. Add your name and register. All right, and since it's going to be, I think, online, I think it'll be available to anyone in the world. How's that? Then this came up on Facebook. Everybody's getting in on this solar eclipse action. How wonderful is that? Do be careful, though, because there are some people out there who might want to sell you something that's supposedly safe for using to look, and it might not be. All right, so just be aware and use caution. Buy from a reputable vendor, that kind of thing. Okay, so RV intent interest form. It's basically just a form. Where is it? I think Facebook had where, but I don't see where on here. Oh, here it is. Canton, Texas. We have another eclipse. Oh, but this is really cool. Atlas Obscura has eclipse images throughout history. And I thought this was really interesting because, of course, at one point they didn't have like a standardized, viewing material. And they even say here at the bottom of this one, these are a group of nurses observing a solar eclipse in England. Oh, I thought they said that there was no. Oh, I think that was Dave. Dave mentioned that they weren't uniform. They weren't standardized. And a little bit of article for that. And then some more pictures. But, we've been fascinated by solar eclipses for a very, very long time. All right. Any more pictures? Yep, there we go.
I like the ones the kid was wearing.
Yeah, they look pretty cool. I've seen one where you put it through a paper plate. So you get the shade from the plate around your face. That's pretty cool. Look at these. Aren't these neat? Yay, cool. Even policemen watching the eclipse in Berlin, 1914. All right. So that is Atlas Obscura, Century of Eclipse Watching. I bet you could do a search and find that too. All right. And then SciStarter has this nice event coming up next Tuesday as well. The 26th, April 16th. All kinds of different activities and lectures that you can attend. Again, I believe this is online. Yep, there's the form for the like a Zoom. Yep, a Zoom.
I don't know when this came in because
I was. Tell us who.
Yeah. Who's good? Sorry, she was talking about so many different things, and I didn't see this right away.
Oh, the
Yeah.
astronaut one, maybe?
Yeah.
Tell us. Thank you.
Yeah.
All right. Yeah, because I'm over here. I
And
can't see the comments.
And I had my face on my computer
Yeah.
getting the links.
I thought this was pretty neat. The Great 2024 Eclipse Guide, US only. They do have a link if you are somewhere else to go over there. Let's see what happens. Oh, it is covered. A little bit more money. That's all. All right. So this is shop at sky.com. And I bet if you did a search for 2024 Eclipse, you would get there. All right. And I thought this was kind of neat. And oh yeah.
Janie says, fun old pictures.
Yes. Oh, yeah. Happy St. Patrick's Day.
Yep.
Thank you, Jenny. I really enjoyed those pictures. That was really neat, too. So this is from Moon Rocket. We've seen them before. From supermoons to eclipses, top 6 moon events to watch with your kids in 2024. So if you've got kids, what a great way to enjoy time with them. Full moon, supermoon, blue moon, new moon, partial lunar eclipse, total solar eclipse. I noticed they did not have the mini moon, though, so maybe that's too new for them. All right, and then I found this also on Facebook. Everybody's getting into the action, including this O.E. Meyer Company, industrial supplies, welding, gases, propane place. And when I got there, it was a little disappointing, but probably somewhere on here, because what they say is pick up your best welds shade 14 hardened glass filter plate today to view the eclipse. Only $4.08.
And that'll protect your eyes from the light of the sun and the sun falling on you because it's hardened glass.
Right. So oemeyer.com, I think somewhere on there. Well, they got more stuff, but I can't even tell.
Yeah.
Where the glasses are.
And they offer a money back guarantee if you are injured by the sun falling on you.
Oh boy. I don't think they do. All right, and this looks
wouldn't matter. They wouldn't have to pay up.
Yeah, you're right. The William Shatner Experience. Now, Legion M has a movie coming out called Just You Can Call Me Bill. And William Shatner is going to have a couple of events. These two happen to be in New York and Los Angeles. And they're coming up soon. So if you're there and you want to go, check it out. March 17th and 18th, New York packages. There are a couple ways to get involved with these events. Here it is. You Can Call Me Bill, the movie, March 17th. It is a little pricey, though. Wow. Although you get to walk on the red carpet and you get VIP screening. There's the New York City weekend with Bill. That's a little bit more, too. So ways to book it. You click on the link here. Then there is Los Angeles on March 21st. That's near us, but it's even more. So I think we're going to skip this one.
Yeah.
So, yeah, a couple different ways to get involved with William Shatner. I just thought this was fun, and it's not eclipse stuff. Well, it's wonderful. Don't get me wrong. But there's been a lot of it. Hatch watch at a California bald eagle nest monitored by popular online camera feed. So if you want to watch some bald eagles in their nest, I think they have said they had three eggs. Three bald eagle chicks could emerge this week from eggs laid in a nest monitored by nature lovers via a popular online camera feed. How cool is that? We can see the bald eagles in their nest. All right. Let's do this one. Yeah. CBS12.com. Again, I would do a search. Yeah, there's a search thing.
Yeah, just Hatch Cam or something.
Yeah, Hatch Watch. And that's in California. So you'll have a time zone and light dark thing going. But it's still, webcams are cool. Here's another eclipse. Imagine that. A guide to harvest hosts in the 2024 solar eclipse path of totality, U.S. and Canada. Now, this one is, and I really literally just found this a little bit earlier today. Well, okay, free of charge. Oh, I guess to learn about their campsite. Cool. Okay. So, yeah, lots and lots of possibilities for the eclipse this year, including this one, Journey Homeschool Academy. Free homeschooler's guide to the Great North American Solar Eclipse on April 8th. This one is journeyhomeschoolacademy.com. And I think it's great. So there's lots of ways, not just lots of options, but lots of different levels of available activities and stuff.
Jay, love the bald eagle camera. 3 eggs past 46 days normal hatch time.
What? They're
past the 46 days normal hatch time.
Oh,
so they haven't hatched yet.
Okay, I see. So did you know about that before, Janie? Interesting.
Yeah.
All right. Is the other one you saw already?
Yeah.
Yes. I got one more here. And oops, sorry. I usually have it at the top. GalaxyCon, San Jose, I believe. This is somewhere you go.
Yes.
It's a live event. That's August 16th through 18th. We don't really have these in any particular order. I just found this, I think, as we were getting ready for tonight's show, like, between 8 and 9. So, yeah, I don't know much about it, but I guess it's a con.
Yep.
Yes. Like
sci-fi con, yeah.
Yeah, science fiction convention.
They're coming back since COVID. I mean, I've seen a few others.
And that's in San Jose, California. Let's see, what's our galaxycon.com. That's GALAXY CON.com. Sorry. All right, so it's a 3-day thing. Kind of a regular old conference, space science fiction convention.
Yep.
All right, so that's all I got here. That's all I got.
Okay.
All right, you want to take us out?
Okay. If you or someone you know has done something interesting involving space exploration, science, or astronomy, we'd love to share our live. Join us again next Friday, March 22nd. Our guest is Stephen Eckroad. He's a sci-fi author and a scientist. Pam picked up his books last weekend. Got 4 books in 4 hands here. There they are.
I can't wait.
So,
and he's definitely a scientist. Let me find a good part of this, because I took a video, but I couldn't figure out how to give you a short little snippet of it. Oh, yeah. Thanks, Don.
Thanks, Don. Yeah.
We really appreciate you being here, and that really makes it so much better. What does he say? Scientist, engineer with a degree in physics and practical expertise in emergent electric power technologies.
Yep.
So, teaser until next Friday.
Yep.
So let's do a shout out. Dawn and Janie and Scott was here. And Cliff just got to Canada.
Yep.
He just got to Canada.
Yeah.
So he's not
here. Here's a greeting to Cliff in Canada. G'day, eh?
We had a couple more people. I don't know how to say this. Sathi Gan Iyer and Neox.
Yep.
And did we get everybody? Janie?
Yep, you got Scott and Janie and Don. Yep. Yeah, and me and yeah.
We're so glad you're here. We really appreciate it because it makes it so much better.
Yeah.
All right. Anything else from you?
Nope.
Anything else from you? We'll be watching afterwards as well for your comments. And I know Cliff will probably watch the show later. I think, if he wants to, he'll be one of the hosts next week.
Yep.
I did get a guest, so the idea he had for a guest, we'll have to wait. So that's okay. I think it'll be me and Cliff, and then the following week it'll be Jeff and Cliff. I know Dawn and I talked about some solar eclipse stuff, so it'll be the 29th or what's after that, April 5th. We'll have to talk some more, Dawn.
Yeah.
So, welcome to the new people.
Yeah.
Absolutely. All right. Thank you so much, folks. Yeah.
And if there's anything that you guys want to hear about here, we're always looking for ideas for shows. And heck, I might get an idea that I don't have to get from seeing something from Anton that sends me off on a tangent.
That's okay.
Yeah.
He's really good.
Yeah, he is. I highly, for the new people here, look for Anton Petrov on YouTube.
I'm going to type it in for you.
Because
that is how you spell that.
Yeah, because he does really good stuff.
And most every day, I think.
Yeah, he's really prolific.
Got something.
Yeah.
Very many days of the week, whatever it is. I don't know exactly. 8
to 12 minutes episodes almost every day.
Yeah.
Yeah.
And they're highly produced, not like us. We're just.
Yeah.
We just come on here and talk to you.
Yeah, he's got production value. And,
yes.
And he is a scientist, so.
Yes.
So
All right.
he knows what he's talking about.
Yes.
We don't.
Yeah,
That's our
well,
charm.
We love learning. That's what we really.
Yep.
And after that, we kind of know stuff. So yeah.
Yep.
Okay.
Okay.
Thank you so much for being here, everybody. We really appreciate that, and have a great week.
Yep.
We will talk to you and Stephen and I think Cliff.
Yep. Okay.
Good night.
Good night.